thing I should say is I only have one monitor, so if I'm sharing my slides, um, I don't think I can read the chat box or anything.
Oh, I'll watch that for you.
Yeah, if you watch that, and if anybody has questions while I'm talking, let me
That's a
know.
good that's a good
So
idea.
maybe you could just kind of moderate the questions or
Sure,
whatever. That would be really helpful.
sure. Well, let me introduce our speaker. Our speaker is Professor Nathaniel Throckmorton, a 2006 graduate from UW Stevens Point in mathematics and economics. And he is Associate Professor of Economics at William and Mary after having gotten his PhD at Indiana University in Bloomington.
Okay. Thanks a lot for inviting me to give this talk. As I said earlier, it's the first seminar I've done this semester. So I'm really excited to do this for um, my my college, and I graduated what 14 years ago, so it's been quite a while. So I'm glad to be back. Um, I thought I would just have a talk that caters to both people in math and economics. And my goal is to sort of give an overview of things that I use, tools that I use in my research. At a higher level, I'm not going to go into too much detail, I hope. I was trying to avoid too much detail anyways. And if you have questions during the talk, just type it in the chat box or speak up, I guess, and I can't see you, but I'll do my best to answer your questions as we go. I'll also post a link to these slides. I put them on my website here. So, okay, so I just wanted to start with economics in a nutshell. And I guess when I introduced economics in my principles classes, I kind of always ask the question, is it worth doing or making more of something? So we're talking about an activity, how to allocate your time, or how much of something to produce as a company or whatever. So to answer that question, we're always doing a cost benefit analysis, and sort of like the hallmark of economics is like the market, and in the market you have price and quantity, you have coordination of supply and demand. We call that an equilibrium. So that's sort of like the center of every economic model that people use, whether it's on the micro side when you're talking about a firm or industry, or on the macro side if you're talking about the national or global economy. There's some kind of equilibrium concept, some kind of cost benefit analysis going on. And then my second question usually is like, why do economists have jobs? So we have this market. So should a market solve all our problems, you know? And the fact is they don't. There are market failures. And one of the big ones that's we're very aware of at the moment is that if you're making stuff, it creates problems such as emitting pollution and causing global warming. And so how do you come up with a mechanism or a policy to address this issue of too much pollution or greenhouse gas emissions for the global economy? So this is why economists might have a job, is to help try to come up with policies or things to address these problems. And what can we do about these problems? I already answered the question. We can maybe legislate some solutions, or maybe have an administration that uh, agrees to reduce greenhouse gas emissions or something. So uh, that's economics in a nutshell. To me, it's very very high level, broad definition of it, but that's kind of how I think about what we do. And then so I want to get into my area, which is macroeconomics, and then relate that to the other side, which is micro. So on the micro side, we're usually talking about one market or an industry and thinking about equilibrium, prices and quantity, the price of a good and how much a good is being produced in that market. Because we're talking about healthcare, the price of healthcare, how much healthcare services are provided to people. That would be a microeconomic thing. Macroeconomics is having many markets, and many markets could be like households supplying labor, firms employing household labor, governments, enacting policies that maybe provide unemployment benefits or something and affect the labor market. So you have many markets. That'd be, I just was talking about labor, but you could also have capital markets, buying and selling capital between companies, or financial markets, financial assets. So you have many different goods, markets for those goods, the prices and quantities in each market, and that gives us kind of a general equilibrium. You have equilibrium coordinating across many different markets. So that's what macroeconomics at a high level is. And it's the study of national and global economies. And I'm working with time series data, so thinking about variables over time like the unemployment rate or production, gross domestic product, inflation, interest rates. And so I usually think about time frame. Are we thinking about the short run? Are we thinking about the next recession? Are we thinking about how long this recession is going to last? That's kind of a 1 to 2 year horizon. Are we thinking about the medium run? I think I lost my, there we go. Are we talking about the medium run, maybe something between a 2 and 5 year horizon? That's kind of the labor market story. When people lose their jobs, it takes a long time for them to find new work. Maybe they have to get new skills or move to a different part of the country. And so labor markets take a long time to recover. Or we're talking about the long run. Long run would be like economic development or growth if we're thinking about a low income country enacting policies to incentivize investment and entrepreneurship and intellectual property or something, and growing over 5+ years, 10 years, 20 years, very long term. So it's useful to think about when we're asking research questions in macro, what kind of time frame are you thinking about? I've recently working with labor market data and models trying to explain movements in labor market stuff. And so I'm working with time series data that's a function of time. Here I've got the unemployment rate. So the unemployment rate is what % of the labor force are people without jobs that are looking for work. And I got this data from Fred. Fred is a great resource for macroeconomic data in the United States. I'm plotting data here from 1950 to 2020. It's a function of time, and the gray regions here are the recessions in the United States, and you can see unemployment increasing during recessions, and then gradually falling back to something kind of a minimum, a local minimum, and then the recession hits and unemployment rises and it gradually falls back. So this is kind of the 2 to 5 year horizon I was talking about. You have this short recession, maybe it lasts for a year where unemployment's rising, and then it takes a few years for unemployment to fall back down to where it was before the recession. And so our goal in macroeconomics is to kind of understand the properties of this data. What's the volatility? Does it have skewness? This feature here where it rises fast but falls slowly is kind of something we might want to explain. And so we're going to write down an economic model that would hopefully make predictions that can predict the properties of this data. The volatility, the skewness, the asymmetry, and how fast it rises and how slow it falls. So that's kind of what I've been doing recently, and I hope to tell you about some of the tools I've been using, mathematical tools I've been using to address those questions. This is some terminology that shows up a lot when we talk about macroeconomic models. So these are mathematical models. I mentioned general equilibrium already, where you have multiple markets and you have these markets coordinating the prices and the quantities. And usually in macro, we have, just generally speaking, a capital market where we have machines and buildings that are used to produce stuff, and labor markets where you have people working and supplying their labor, and capital and labor are complementary. So people work at machines and increase their output. So you have these two markets coordinating. So if they're in equilibrium, we call that a general equilibrium. Another feature of models is whether you're thinking about, in terms of time, a static model, which is just basically doesn't have time. It's kind of long run averages. So if you have time series data over the last 70 years or whatever, you're just looking at the 70-year average of the data. That's more used in like growth economics, where you're thinking very long term. You're thinking about growth over 10 or 20 or 30 years. You're not too worried about short run transitions. So people do use static models for growth economics versus dynamic models. I usually work with, this time series data, and I'm looking at the short run variation in it. So I want a dynamic model that has time in it, that can make predictions at this 2 to 5 year horizon, or even shorter. So that's kind of a dimension in macro model, static versus dynamic. And if it's dynamic, I mean, either way, if we're talking about long run averages or we're talking about short run fluctuations, we're still using time series data to try to understand the time series data. Another dimension in modeling is whether the model is stochastic or not. So a deterministic model would be there's no exogenous or random variation in the model. A stochastic model has like shocks that hit the economy, and these shocks have a probability distribution, and people don't really know what's going to happen, you know, next quarter, next year, next in 2 years. And so you have this kind of a random variable in the model that introduces just variation that's uncertain. So I like to think about my macro models as kind of like little economies, little simulated like artificial economies that I'm living in. And so I often think of myself as like I'm the household in the model, and I have to make forecasts about the future because random things are happening in the future, and I'm not sure what's going to happen exactly. So I call that a stochastic model. And then if you combine all these words together, dynamic, stochastic, general equilibrium, or DSG models. These are kind of the workhorse models of many policy institutions, such as the Federal Reserve and other central banks around the world. Congress uses them on the Joint Committee on Taxation and the Congressional Budget Office, and the Brookings Institution, the IMF, and the World Bank. So we got think tanks and other banks using DSG models. So they're dynamic. They can make predictions about short run variation in time series data. They're stochastic, where things are uncertain and you have randomness in the model. And they're general equilibrium. So they have multiple markets coordinating together, trying to find an equilibrium. So this is a tool that we use in macroeconomics, and there's a lot of math that goes into using these models. So that's what I'm going to get into next. So my summary of the math I'm going to present is just, we got some functions, and the functions are really basic that we usually work with in macroeconomics. So that's going to be pretty simple. Then we have some calculus where we can take a dynamic model and solve for the equilibrium in the model, just with first derivatives. We can have some more calculus. You can take a nonlinear model and linearize it, and linear stuff is very easy to work with. That's just the first order Taylor expansion or Taylor series. So you can use some calculus to linearize models. If you don't linearize your model, you could approximate the nonlinear system. And so what I do for most of my research is numerical analysis, and then I'm using the computer to try to get an approximation of the nonlinear equilibrium system. And it's just a system of equations, but it's nonlinear. So what we're doing with this numerical analysis is I'm trying to solve for a function, and I'll show you what kind of functions I'm solving for on the computer. And then there's some statistics, or what essentially is this linear algebra, is estimating these models. So once we have a model and we can solve it, we can then take it to the data and ask how well it does at matching and explaining features of the data. So I'll talk briefly about estimating at the end. All right, any questions before I get started on the math stuff? Can you still hear me? Okay. Sometimes it's like, yeah, okay, good, thank you.
Yeah, we're good, no questions.
Okay, great. Okay, so some functions. So actually the kind of functions we use at first are really simple. So this is the most used function in economics. I'm letting you in on a secret. Okay, so this is a concave function. It's this is actually the natural log. The inputs are positive because we're going to talk about consumption of goods or capital, or machines and buildings. We don't have negative goods and we don't have negative capital, so we're always operating on the positive support here of our input is a positive thing, possibly zero, but usually positive. And the function is increasing in this input. So if we're thinking about a person and they're consuming goods, the more goods they consume, the happier they tend to be. So it's increasing, but it's increasing at a diminishing rate. So, the first pizza slice I eat makes me really happy. The second slice, a little bit more happy, but not as much as the first slice. third piece of slice, a little bit more happy, but not just a second slice. So I've got this this function that describes my happiness from eating pizza, and it's diminishing over time, diminishing as I eat more slices of pizza. So that's a basic function that we're using in our macro models. It doesn't have to be log, but log is a pretty common function that people use. So I was saying happiness, but we also just call that utility. What's the utility of consuming goods? And so this is a utility function. It gives us that. And so with that in mind, I'm going to introduce our first dynamic model. And you have to imagine Tom his airplane has crashed and he's the only person on an island, and he's got to look out for himself. So he spends his time gathering and making stuff. So he might gather FedEx packages that have been, fallen out of the plane, wood, coconuts, things like that. So if he gathers some coconuts, he can eat them, and that gives him some happiness. If you gather some FedEx packages with some useful tools in there, that can help him gather more stuff or make more tools that he can use for gathering and making stuff. We're going to say Tom has an income. It's a real income. It's the stuff that he's gathering and making. I'm going to call that Y. And then he can take that income and split it into two types of things. He can split it into consumption things or investment. So consumption is for today. If Tom collects a coconut, he can eat it or drink the coconut milk, and he gets happiness today, but he's not investing. So he's not investing for the future. He could have spent that time making a tool like an axe, and then he'd have that axe for tomorrow and the next week and the week after that to help, chop wood or do something like that. So that would be investment, using his time to build an axe or something. Tom gets happiness or utility from consumption. And I showed you on the previous slide, the more he consumes, the happier he is, but at a diminishing rate. And then Tom is on this island for a while. Actually, I'm going to say he's going to be there forever, for the rest of his life. And so he can consume today, or he can wait to consume tomorrow or next week or 2 weeks from now. But future consumption isn't as valuable as it is today. If he eats a coconut today, it feels really good. But if he has to wait 7 days to eat a coconut, that's not so great. He's not so happy about that. So he's going to discount future consumption by this parameter beta. And beta is going to be a number between 0 and 1, so that future consumption has less value than current consumption. Any investment he does, any things that he gathers that are useful tools or whatever, will be productive in the next period. So tomorrow he can use the axe to chop some wood or something, and I can help Tom get or make more stuff. And so potentially, if he makes something, an elaborate machine, it can make him very productive. Maybe he makes a machine to harvest coconuts or something, so he can gather a lot more coconuts than if he just went by the palm tree and collected them one by one or something. So investment, you want to think as being productive. It can help you increase your income in the future. And then in terms of the deterministic versus stochastic side of this model, I'm going to say Tom knows everything. He's all knowing, and so the model is deterministic. There's no randomness. There's no uncertainty. Tom is just amazing. So here we got a dynamic model set up in kind of words, and I'm going to show you some equations to describe this model.
Hey, Nate.
Yeah.
Quick question. Beta, the discount for future consumption, do you have to use bigger betas for Americans than you do for other people?
Yeah, they're more, could be. So, countries differ by how much capital they have. Countries with a higher beta tend to have lots of capital because they're kind of forward-looking. Countries with less capital might have a lower discount factor, and they don't save as much. So yeah, you can have different betas for different countries. And when in macroeconomics, we usually associate beta with the interest rate, so we can measure the interest rate. It tends to be
I just view us as consume now kind of culture.
Yeah, so we would actually be low beta then. And a lot of us are even within a country, you can have people that have high betas and like to save for the future, and low betas that don't like to save for the future. Um, and yeah.
Makes sense. Thanks.
All right. Any other questions?
Yeah, so from the last slide for U and C for, oh, no, after that.
Oh, yep.
Yeah, I think it's, okay, it's the bullet point in the middle. Tom gets happy / utility from consumption.
Yeah.
So what are we taking the derivatives for?
Oh, so the utility function I'm calling U is a function of consumption. So it's increasing in C. So the first derivative, if it's positive, means that utility is increasing in C in consumption. And the second derivative, U double prime, if that's negative, then utility is increasing in C at a diminishing rate. So that was the pizza slice story I was telling. Second slice of pizza makes me happier, but not as much as the first, and the third slice of pizza makes me a little bit more happier, but not as much as the second.
I see.
So the first and second derivative give us that property.
And then would this be like a DSGE model? Or is that different?
It will be. It's not stochastic yet, but I'll add some randomness later as an extension.
Okay, so this is like, I guess, like intermediate steps to get to the
Yes.
model. Okay.
Yeah. Okay, so to set up, this is going to be a maximization problem. So Tom's goal is to maximize his lifetime happiness. He's going to be on this island for a long time, so he wants to make the best of it. So I'm going to call little t today, like when Tom's plane crashes, and from time t he has this planning problem. He wants to plan for the future and maximize his lifetime happiness. So he starts consuming and investing today at time t. He lives forever. Every period, whether it's a day or a week, let's say it's a month actually. So let's say every month he's got this budget constraint. He has income y t plus j, and he can divide that income into consumption and investment goods. And j here would just kind of index time. So if j is 0, we're at today. If j is 1, we're next month. J is 2 months from now, so on and so forth. So that budget constraint Tom faces every month. And then Tom is going to choose a sequence of consumption and investment over his lifetime to maximize the present value of his lifetime happiness or utility. So the value for his present value, lifetime happiness, or utility is this infinite sum of all utility for consumption every month from today through the infinite future, discounted to the present by beta. And the further out you go, the more discounting there is. So if your 1 month consumption 1 month out is discounted by 1 beta, consumption 2 months out is discounted by beta squared, consumption 3 months out is discounted by beta cubed, so on and so forth. So that's his objective function, really, is to maximize this object. And he's going to choose consumption and investment to maximize this thing. So Tom's gathering and making stuff. Some of it's investment goods, some of it's consumption goods. Any investments he makes helps produce more stuff in the future. So he's going to have a production function. This production function, here's his income y, is the function of the things he's invested for the future, and it's raised to this power alpha. And now alpha is going to be a parameter whose value is between 0 and 1. So this is also going to be a concave function whose first derivative is positive and second derivative is negative. So this production function has the same shape as the utility function and the same idea. If you invest more, it's going to increase your income, but if you continue investing, it's going to increase your income at a diminishing rate. So this is the same assumption that we made about the utility function. And then you can combine this budget constraint, consumption plus investment goods equals this production function. You can plug this into the budget constraint for yt plus j. So that is a maximization problem. Maximize present value lifetime utility subject to this budget constraint. And this budget constraint holds for every month now until forever.
So does the coconut part of the analogy factor in here or not so much? You know, like the coconuts are kind of provided by the island. Are we ignoring that kind of factor?
Yeah,
Do you know what I mean?
I'm
Okay.
kind of thinking there. Tom has like, maybe he works 12 hours a day. He's got some time, and so he can use his time to either create investment things like axes or
Okay.
Or chop wood maybe, and that wood's available for making fires tomorrow, something like that. Or he could spend his time collecting coconuts, and that would be a consumption good. Maybe he has some tools that increase how many coconuts he can collect. And so it's like his income's going up because he can collect more coconuts in the same amount of time.
Yeah, that makes sense. Thanks.
Okay, cool. So to solve this maximization problem, we're actually going to write it as a Lagrangian. So this is just a way to write a dynamic optimization problem. And I'm just doing this kind of at hopefully at a higher level. Don't worry too much about how you actually go about setting these up. It's just kind of like FYI, this is what this looks like. So in order to do this Lagrangian, I'm going to introduce a Lagrange multiplier, lambda, which is non-zero if Tom's budget constraint binds. So that means he has his income and he uses all of it for either consumption or investment, and there's nothing left over. So that's a good thing, right? Tom wouldn't want to have, things that he collects and just lets go to waste, like collect 10 coconuts and don't eat them. Well, there's no point in that, right? So Tom's going to be doing the best if his budget constraint always binds, and he uses all the income that he earns. So that's that lambda kind of measures how much that budget constraint binds. And so to write a Lagrangian, we've got the script L or whatever, this stands for Lagrangian, is the infinite sum of the present value of his utility. And then I'm going to add in here his budget constraint solved for 0. So this is income minus consumption minus investment, and it's multiplied by this Lagrange multiplier. And so Lagrangians typically, this is how they work, that you have a number of constraints, and this problem only have one constraint, but you could have 2 or 3 or 4 constraints. And each constraint you solve for 0 and then multiply by a Lagrange multiplier. I'm not going to get into why this works, but this is how you'd set up this dynamic optimization problem. And then there's kind of a shortcut we can take, because Tom lives forever. His planning horizon is always the same. It's always infinite. And so the solution to this optimization problem is actually a time invariant function, which means that no matter what month it is, this month, next month, 2 months from now, 3 months from now, given his investments, KT minus 1, the function that describes his consumption is always going to be the same function. It's always going to have the same shape, and it's always going to have the same relationship to the input KT minus 1.
Is that Lagrange multiplier then, is the meaning of that like the value of an extra hour or something like that?
Yeah, I think it would be here, yeah, like an extra unit of income. Yeah, it's the value of an extra unit of income, and it tells you how much it would add to his utility. Yeah, that's right. So the shortcut here is because Tom lives forever, his planning horizon is always the same. We're actually solving for a function. It's going to be a function that describes his consumption as a function of how much he's invested for the next period. And so all we really need to do, we can get rid of this infinite sum. We can just look at his utility today plus this Lagrange multiplier today times his budget constraint today plus the next month. So discounted to the present by beta, next month's utility from consumption next month plus his budget constraint next month times this Lagrange multiplier for the next period. So we've basically taken an infinite period optimization problem and reduced it down to 2 periods here. And that's good enough because his planning horizon is constant. Alternatively, if you were to have like Tom's only going to be on the island for a year, 12 months, so his planning horizon is changing. 1 month goes by and he's got 11 months left. 2 months goes by, he's got 10 months left. Then that complicates things quite a bit, where your planning horizon is changing. So then his decisions as a function of his investments each month actually are changing. The shape of them are changing. So it's not time invariant in that case. So the infinite horizon thing looks scary at first, but it's actually a simplifying assumption, and that we only need to look at basically the today and tomorrow. Okay, so now for some calculus. We have written our whole optimization problem as this expression here. All we want to do is maximize this Lagrangian, choosing consumption and investment to maximize it. So all we need to do is take two derivatives. We can take the partial derivative of Lagrangian with respect to consumption today. And what you get is Lagrange multiplier equals the first derivative of the utility function. We call that U prime is called the marginal utility of consumption. So like Professor Felt asked, what lambda is really telling you is the value of an extra unit of income. So if Tom has one extra thing, he values that at, the consumption value of it. So he gets one extra thing that he could consume possibly, and that would add to his happiness, this U prime CT. So that's the way to interpret that Lagrange multiplier. And then the other derivative we'll take is with respect to investment, KT here. So the first derivative of Lagrangian with respect to investment, this is the expression, and then we'll take first order conditions. So we set equal to 0, and then we can get an expression that relates the current Lagrange multiplier with the future Lagrange multiplier. And then I substituted in here this first derivative, the first derivative we took, substituted out the Lagrange multiplier, and I have an equation here that relates consumption today to consumption tomorrow. And that's what's really important about this this whole exercise is relating current consumption to future consumption. So in macroeconomics, the whole idea is how do you allocate consumption across time? So you have machines and buildings, you can produce all kinds of goods and services, and some of those are consumable that give people happiness. And so the macroeconomy is allocating consumption over time, essentially. And so this equation is kind of the first pass expression of that that allocation. Well, another great thing, another simplifying assumption here is utility was concave, and so we don't need to check the second order conditions. So we always learn in calculus to check second order conditions to make sure this is actually a maximum, but we don't need to do that here given our assumption about the utility function. So this equation describes the maximum to this optimization problem. It has an interpretation in economics. If you've had an economics class, you have supply equals demand. The supply curve can be thought of as a marginal cost curve, and the demand curve can be thought of as a marginal benefit curve, where these two things are equal as the equilibrium. And so this is actually a dynamic equilibrium equation. So we've got something today equal to something in the future, and we can interpret these as benefit versus cost. So this equation tells Tom how to allocate consumption over time, the solution to his optimization problem, to maximize his happiness. The left-hand side is the benefit of consuming one more thing today to Tom. And if he consumes one more thing today, then he's giving up something. Instead, he could have had some kind of investment that would have helped him be more productive in the future. So what does Tom actually give up? Which that's the right-hand side of this equation, is the value of investing today in tomorrow's production. And that value is given by this expression here, which is then if you increase future consumption, you'll value that at the margin utility to consume out of it. So that's what gives them happiness is consumption. So you value future income at the margin utility to consume out of future income. That's the first derivative of the utility function, and as a function of future consumption. And then the beta is here because that hasn't happened yet. That's in the future. And so he doesn't value future consumption as much as consumption today. And so he discounts that to the present by this discount factor beta. So this is, again, an equation that tells Tom how to allocate his consumption over time. And so in the macroeconomy, we've got lots of Toms, and we've got lots of households, and we've got lots of firms, and we've got lots of machines and buildings. And so we're thinking of this kind of equation for lots of people, lots of households, not just for one person stranded on an island. Just to summarize the system of equations, I want to first assume that the utility function is the natural log of consumption. Then you can take the first derivative, that's 1 over CT. The whole dynamic model is described by these 3 equations. You've got the budget constraint, you've got the production function, you've got this consumption Euler equation. The Euler part is just the fact that it's got, it's a dynamic equation in consumption. So consumption today and consumption tomorrow. So you have these 3 equations, and you've got what are called choice variables. Tom gets to choose how much to consume each period and how much to invest each period. And then you've got a state variable. When Tom wakes up every month, he's got a bunch of tools and stuff lying around that he can use to produce stuff. So that's that KT minus 1. And so every month that Tom wakes up, he wakes up with a bunch of tools lying around, a bunch of packages he's opened that could help him collect stuff and make more things. And then he gets to allocate his day making either consumption goods or investment goods and planning for the next month. And then with all systems equations, whether they're linear or nonlinear, we should have the same number of variables as equations. So when it's a dynamic system like this, I'm just keeping track of the time t variables. So the time t variables are consumption today, investment today, and output today. So we got 3 variables, and we've got 3 equations. So that's good. That means there could be a solution to this system of equations. Not guaranteed that there's a solution, but there could be. I guess I've got about 20 minutes left. Is that right, Professor Felt?
Yeah, sure.
Going to 7? Okay.
Mhm.
All right, so I'm just going to kind of skip through this a little bit. This dynamic model actually has an analytic solution, closed form solution that you can do by hand, which is really neat. You can take that equilibrium equation and do some rearranging and substitution. And my favorite algebra trick, add the number 1 to both sides. And then you can get this recursive equation in this ratio y over c. So you got y income over consumption today equals 1 plus alpha beta income over consumption tomorrow. It's a little recursive equation that you can forward substitute. And if you forward substitute this thing for infinite periods, you get a nice geometric series. 1 alpha beta to the 1, alpha beta squared, alpha beta cubed, alpha beta to the 4th, so on and so forth, alpha beta to the infinity. Because both alpha and beta are between 0 and 1, the product is between 0 and 1. So this infinite series has a finite value. So we can evaluate this geometric series. The ratio of income to consumption each period is the optimal ratio of income to consumption each period is 1 over 1 minus alpha beta. So this is a solution. Solutions to macro models and dynamic systems would just be a function of parameters or state variables. State variables that you know going into today's decisions, and parameters are just features of the model that you take for given, take as given. So the analytical solution to this model, we can rearrange things, use the budget constraint, use the production function. We can express Tom's consumption each period equal to 1 minus alpha beta, so just parameters, times kt minus 1, which is a state variable, so the number of tools and machines that he has lying around, raised to the alpha. So this is a function, the consumption function. How much should Tom consume each day is given by this. You know, this is the recipe for maximizing his happiness. And if you plug this into the budget constraint, you can also solve for investment. So investment today is equal to alpha beta times investment from yesterday to the alpha. So that's an investment function. So the solution to this dynamic model is actually a couple of functions. Consumption and investment as a function of the state of previous investment. And this is what a solution looks like. It's choice variables as a function of state variables and parameters. Now, a lot of people call these things policy functions or policy rules. And that's kind of confusing because in macroeconomics, we also talk about like tax policy and spending policy and all kinds of policies, you know, health policy and education policy and all kinds of policies. But the idea of calling it a policy function is that Tom has policies. He has a consumption policy. You know, given so much investment he's made, he'll consume. His policy is to consume according to this equation, or invest according to this equation. So, this is some terminology. Now, this model has an analytical solution that we can solve for by hand. It has a nice geometric series representation, and these solutions are pretty simple. But typically, closed form or analytic solutions are not available. This model is easily made complicated if you just allow investment to depreciate every period. Then there's no closed form solution. So you just add one parameter. If some of the tools break, for example, there's no longer an analytic solution, which is kind of crazy, but that's the way it is. So if there's no analytic solution, you have to take some other shortcuts. And so I'll just talk now about shortcuts that people take. You can take the nonlinear model and you can approximate the model. You can either linearize it or use some other approximation. So a lot of people linearize their models in my field in macroeconomics. That's because we know a lot about linear systems. We can solve linear dynamic systems pretty quickly, very quickly, and we can also figure out whether they have solutions, if a solution exists, and whether it's unique or not. So linearization is one trick that people use to work with dynamic models. Now, if you linearize the model, you might be removing some nonlinear or higher order relationships between variables that could be interesting. And my whole research agenda in the last 7 or 8 years is working with nonlinear models that maintain those relationships. And so I'm not linearizing stuff in my research because I'm trying to ask, do these nonlinear relationships actually matter? The other option you have, if you don't have an analytic solution to your model, is to approximate the nonlinear solution numerically. And that's what I do. So I was going to talk a bit about both of these things. In terms of linearizing a model, you can use Taylor series to approximate your model. So you can, a linearized model is just a first order Taylor series. So it's just the first term of the Taylor series. Here's the univariate version of the Taylor series. You have the multivariate version of a Taylor series, which is useful because our dynamic models have at least 2 variables usually. This one has 3 variables: consumption, capital, consumption, investment, and income. So here's an example of linearizing a function with two inputs. The dynamic models are going to be stable around a long run mean. So it's called a steady state. So a Taylor series is an approximation around a point. In macroeconomics, we're going to approximate the model around the long run average. So if I showed you the unemployment rate in the previous slide, long run average unemployment rate might be 5 or 6% over time. I can linearize the model around that point. And it's helpful to define a percent change in that case, because let's say I have income, I have a long run average for income, and the model dynamically the income is going to fluctuate around that long run average. Then I can summarize its fluctuations and percent changes from that long run average. So I'm going to define this variable x hat. A hat is a percent change from the long run average of some variable. So just to quickly do this, I won't get into too much detail, but you can take the equilibrium equation. It's got time, time today, tomorrow, capital, investment, consumption, income. If you took this equation in the long run, I would say this is long run investment over long run consumption. So for the rest of Tom's life, for example, long run income over long run consumption. I'm going to linearize this equation around these long run values. So you can take a first order Taylor series of both sides of this equation. Each side has two inputs or variables. And so this is the Taylor series of this equation. And then I can use my definition of percent change and substitute out for that. And so this nonlinear equation up here simplifies to a linear equation. The percent change of investment minus the percent change of consumption today equals the percent change of income tomorrow minus the percent change of consumption tomorrow. It's just it's a very simple linear equation. This is the nonlinear version of it. So you can work with this linear system instead and ask, what is Tom's choice for consumption as a function of investment, or today's investment as a function of yesterday's investment in this linear model. People work with linear models because we know a lot about linear systems. We know how to get their solutions quickly. We know if solutions exist and whether they're unique or not. You can do higher order Taylor expansions, so including the second, third, and fourth terms of the expansion and cross terms in the series. There are numerical ways to do that called perturbation methods. These solutions can get messy very quickly because you have a lot of higher order terms and cross products and all kinds of crazy stuff. And so sometimes they make some very weird predictions that aren't very useful. But you can do that. If you're not going to linearize or use a higher order Taylor series to approximate your model, you can then instead use the full nonlinear model, but approximate a solution to it instead. So instead of approximating the model, approximate the solution. I'll just go over a few numerical tools that I use in my research. The first one is iteration. So we're solving for a function, and we're going to do it recursively. And so this iteratively, I should say, iteratively. And so we're going to have a guess for the function, and then we're going to update it with some information that we got and try it and see if that function can converge to the final approximate solution. So there are a couple different iteration techniques. The function is going to be discrete, and it's going to be defined over a discrete set of points. And so we need some kind of interpolation, because you're going to want to evaluate that function between these points where the function, we don't have a value for the function. So you need some kind of interpolation, and that interpolation depends on how you approximate the function that you're solving for. Really, this numerical analysis really mirrors the analytical closed form solution, and that we're still solving for a function. So we need a way to approximate the function numerically. We need a way to use the model to update our guess of the function until we get the final approximation. And we're also going to have some integrals in the system of equations. So you need some way to numerically integrate to approximate integrals. So where the integrals show up, I'm just going to modify the model to add a stochastic element. So we have the original three equations with a new variable ZT, and ZT is productivity. So there could be good and bad days on Tom's island. So say he has a bunch of tools lying around, and there's a storm, and it washes some of the tools away or breaks some of his machines. So that's a bad day, and he didn't see it coming, so it was totally unexpected. So that's where this kind of randomness comes into play. And so Tom's going to have bad days. Tom's going to have good days where he finds some extra coconuts or something, and he comes home with a bigger basket than usual. so we have this variable ZT to describe kind of the randomness in month-to-month production on Tom's Island. So the ZT variable is going to be unknown in the future. We're not going to know whether it's going to be a good day or a bad day in the future. So you could have a high Z or a low Z in the future. And we're going to introduce what's called an expectation operator. And the expectation operator allows Tom to make forecasts about the future, given information he has at time t. So there's a little subscript t there for the information set that Tom has. So again, ZT is a productivity shock. Tom could be extra productive sometimes or less productive other times. It's a stochastic, it's called autoregressive process. It has a mean that it tends to revert to. So you could have really good days, but you're not going to have a whole bunch of really good days. You can have some really bad days, but you're going to get better over time. You have this big ET, which allows Tom to make forecasts about the future. Expectation operators are actually integrals, so you're going to integrate over the probability distribution of this productivity shock over the bad and good times in the future. And this means ultimately that Tom is uncertain about the future and must forecast future stuff. So we've introduced this random element to the model, the stochastic element that Tom doesn't know the value of in the future. He doesn't know everything now, so he's uncertain about future outcomes, future income, and ultimately his happiness, because he's not sure ultimately how much he'll have to consume in the future. Geez, just a few more minutes. Okay, so everything in the computer is discrete, so we're going to have to discretize stuff. So normally when you have a random variable, it has a continuous support. The computer is only going to understand a discrete version of that. So we're going to take our productivity variable and discretize it. And the way people in my field, at least, discretize these processes is with a Markov chain. So if you've had your linear algebra class and you've learned about Markov chains, you can approximate any autoregressive process with a Markov chain. If the shock is normally distributed, the whole process is actually normally distributed. So you can approximate this normally distributed random variable with a Markov chain. There's two popular methods I just put here. People used to do that approximation. And then the Markov transition matrix is nice because it's a matrix of probabilities, and the probabilities you can use to numerically integrate. So you have future realizations of productivity. You've got their transition matrix from this approximation. You can just use those probabilities to integrate and evaluate this expectation operator. So it's very quick. You're just taking a weighted average of future realizations of productivity. So it's a very quick way to do an integral. We've discretized productivity. The other thing we discretize is the state for Tom's investments. You know, in an analytical setting, this would be a continuous variable, but on the computer, we're going to create a grid for it and discretize it. And so the combinations of investment and productivity, all these pairs constitute the state space of the model. And our goal is to find a consumption policy function, function of these different combinations of investment and productivity that satisfy the nonlinear system that I showed you earlier. And remember, we're solving for functions. So our numerical analysis approach, we're trying to find a function that tells Tom what's going to make him happiest over time. It's the same goal as before when we didn't have the stochastic part. We could do it before by hand as a simple geometric series, but now with the stochastic part, we're going to go to the computer and solve it on the computer. Couple different ways to update your functions: fixed point iteration and time iteration. Fixed point iteration, you use the system of equations to update your guess for the consumption policy function. With time iteration, you use a nonlinear equation solver to satisfy the nonlinear system of equations. Fixed point iteration is a faster algorithm, but tends to be less stable because there are larger errors in each step. Time iteration is slower because you have to use a nonlinear solver to satisfy the nonlinear system of equations, but it's more stable because you're satisfying them at each step, so there's smaller errors. The interpolation part of the algorithm, you need to evaluate your function for consumption between these points that you've used to discretize the state space. And so you need some way to interpolate your policy functions. Um, uh, the interpolation that you use depends on how you're approximating your consumption function. You could use linear interpolation, you could use cubic splines, you could use a polynomial to approximate your function. Popular choices are complete polynomials or Chebyshev polynomials to approximate functions. And depending on how you approximate your consumption function will lend an interpolation method, so you can evaluate your function at values between the points that you've discretized your function at. Just to show you a quick example, I was actually working on this last week. I have a DSG model with employment. So employment really is just a lot of Toms with either have a job or not. And then you got a lot of firms, people that hire, companies that hire people to work. These firms are entering and exiting the market in the model. So they're either choosing to produce or not to produce. There are a bunch of state variables. I've got productivity, just like the last example. I've got employment as a state, and I got the number of firms producing as a state as well. And I've got two policy functions I'm solving for numerically: the number of active firms and the value of these active firms in terms of profits, basically. So I use a very simple numerical algorithm to solve this problem. I use time iteration with linear interpolation, and I use the Rowenhorst method to approximate the productivity process. And my goal was to solve for policy functions that satisfy the nonlinear system of equations. And just to show you an example of what the functions can look like. So this is not your nice concave function, but it's got the two states here on the axes, employment and the number of active firms. And this is the value of active firms producing goods in the economy. And the short of it is that if firms are really valuable, then other firms want to enter, and that reduces the value of existing firms. And if firms aren't very valuable, they start to exit, and then that puts a floor on how valuable these firms can be. And so somewhere in between these two extremes, there's profits can either increase or decrease. And then the other policy function I solve for is how many firms enter or exit each period. And this is the policy function that shows you if employment's high and the number of active firms is high, this is how many firms enter and exit the market. If employment's low and we're in a recession and the active firms are low, a bunch of firms exited, there's a lot of new firms entering because there's a lot of opportunities to earn profit. And so this is a policy function that describes just the change in firms over time. And I'm out of time. So I have a slide on estimation here that you could take a look at. How do you connect the model to the data and try to estimate and test the predictions the models make? There are methods for both linear models and nonlinear models, but you kind of have to tailor your estimation methods to the model you're working with, whether you've approximated the model or whether you've approximated the solution to the model. So just to conclude, macroeconomics and working with DSG models, we're using calculus to derive equilibrium conditions. We're using calculus to approximate nonlinear systems of equations or nonlinear models. Actually, to solve linear models is a bunch of linear algebra. So I didn't get into that, but that's something behind the scenes that people are using in their work. If you're approximating the nonlinear solution to the nonlinear system, you're doing numerical analysis, as I just walked through the bunch of different components that you need to solve for functions of dynamic systems here. And if you're going to estimate your models using some data, you're going to use statistics, which ultimately ends up being a lot of linear algebra. And you can estimate linear and nonlinear models. So I just hope that I've shown you all the different kinds of math that can be used in just my one field. It's pretty exciting that when I got to graduate school, I had all these classes I had taken, and I got to see them all come together. It's just, it was an incredible experience, and I hope that students at UWSP get to experience that at some point as well. So.
And how much of that math would you have understood when you were an undergraduate?
Oh, a lot. Yeah. So I remember my first year of graduate school. I mean, it was kind of more in pieces, you know,
Mhm.
like I knew that I could understand the components. What's really tricky is just bringing it all together. And you know, you have a, you know, these classes and you have a section on this thing and that thing and this thing, and it all seems kind of disjointed. It's really the whole package. Um, the whole toolkit goes into solving these dynamic models. So it's very exciting. Um,
Well, thank you. That was really great. We have time for a few questions if people have some.
I don't have a question, but I just want to jump in really quick and say that if anybody here needs pro events credit for attending, just a private message me quick. It was a really great presentation.
Thank you. Sorry if it was rushed. I didn't know what to cut. So
No, but you know, by the end of any presentation, you've pretty much lost, lost the audience as far as being able to follow you. You know what I mean?
So what I will say is I'll put the link to the slides. Where would be a good place to put that? In the Zoom chat?
Yeah.
Um, where is the Zoom chat?
So if you go down to the bottom in the middle of your Zoom window.
Is it because this is open?
Or if you stop sharing your screen, it might be easier to see.
Right.
something.
Oh, is that? Stop. Sorry, because I'm not teaching. I'm not using Zoom. So. Where's the stop sharing? Oh, there it is. Stop sharing. Aha. Awesome. Okay. Okay, I'll copy this link here, paste it in the Zoom. There we go. There are the slides for the talk today. So you can just Google any of the things that I mentioned. If you're into Markov chains or whatever, you never heard of Rowan horse method, go and Google that. I learned about Rowan horse within the last year, so I was using Towkins before that, and that's why I went to graduate school. So, but it's just a way to approximate these autoregressive processes that we use for time series. So,
So I have a question.
yeah.
Your ultimate goal here, is it to predict the behavior of the individual members of the market, but acting collectively?
So the model does have like prediction and forecasting in it, but I wouldn't say that's the goal. The prediction and forecasting in the model is just really so that people are uncertain about the future and their choices reflect that uncertainty. My goal is to take historical data like the unemployment series since 1960 and come up with a model with reasonable features. Like I showed you, there was in that last example, firms entering and exiting the market, you know, firms shutting down and firing people and that kind of stuff. That's something that we observe in the data, but how do you connect that to actual employment or the unemployment rate? So we need a model that kind of has, you know, households that work, that become employed or unemployed, firms that hire these households, firms that may shut down and fire a bunch of people. We need to have that kind of that story to explain maybe the features of the unemployment rate. You know, this kind of fast increase, the slow decline, the volatility of the unemployment rate, the skewness of the unemployment rate. We're just trying to write down a model that has a nice story that people believe, that can also explain historical time series data. You can take that model and try to make predictions with it, but I wouldn't recommend it. So. So.
Yeah, I think this is really cool to just be able to see all the different parts of math. Like you said, you know, the way we present, it's, oh, here's calculus, here's linear algebra, here, you know, to see how they can fit together just in one place. You know, that's cool.
Yeah, so the first year of grad school, it was an eye opener. I had no idea actually what I was getting into for the most part. I wanted to study economics and think about policy and how to improve people's lives. It was very mathematical, and fortunately, I had my math major going into the economics PhD, and I was able to see these things for a second time and begin to connect things together. Yeah, and it was super exciting, and I'm using it today. So.
Well, we're very proud of you, and nothing makes a teacher prouder than to have a student succeed and surpass them.
And thank you so much for that. Thank you, Professor Felton, Professor McCabe. Both of you just were tremendous as professors. I had so many great experiences working on problems in your classes and being part of math club and doing extracurricular things. It was a great resource. So I really appreciate it.
Thank you.
And your success, my success is your success, basically. You did a great job, I think. So.
There you go.
Any other questions for Professor Throckmorton?
If you go to my website, my email's on there. So feel free to email me. It could be about anything. It doesn't have to be about economics. It could be about jobs or grad school or whatever. I'm happy to be a resource and provide share whatever experiences I've had. So I worked after college for a couple of years in marketing. So if you're into marketing, could talk about that also. So feel free to email me. I'm happy to share. So.
Well, thank you very much. We really appreciate it, and all the best to your family as well.
Yep. Thank you. Thank you for inviting me. I put my email on the bottom there. It's really simple, nat@wm.edu. So.
Great.
All right. Well, thanks.
Thank you.
All right, have a good one. Good rest of the semester. Good luck on finals, huh?
Thank you.
Okay. See ya.
Thanks to everybody for coming.